In this video, I'm going to show you what is a homogeneous differential equation and how we can solve these type of differential equations. A homogeneous first-order differential equation is a differential equation that we can write it in this form. Y prime equals to f of y over x. So if we can write a differential equation in this form, then we say the differential equation is a homogeneous differential equation. For solving these type of differential equations in general, we can use this technique. First, we have to do a substitution. V equals to y over x. So we choose y over x, which appears here, to be v. By this substitution, we can convert a homogeneous differential equation to a separable differential equation. Note that if we choose v to be y over x, we can say, of course, y equals v times x. If we do a cross multiplication here, y equals v times x or x times v. Because we are doing a substitution, we have to replace y prime here. So from this substitution, y prime, if we take derivative from both sides of this relation, y prime, derivative of y equals to derivative of this expression. Derivative of x times v, based on the product rule, is derivative of x, which is 1 times v, plus, write the first function, which is x, times by derivative of v, which is v prime. So we replace y over x with v, and we replace y prime here with v plus x v prime. By doing this, we can convert a homogeneous differential equation to a separable differential equation. Let me show you the first example. Our first example is this differential equation, y prime minus y over x equals to cosine squared of y over x. It is obvious, it's completely clear that this differential equation is a homogeneous differential equation, because here and here we have y over x, and occurring y over x here and here makes it clear that this differential equation is a homogeneous differential equation. And so we use this substitution for solving this differential equation. First, we suppose v to be y over x. By using this substitution, as we see here, y prime equals to v plus x v prime. So we can replace this y prime here with v plus x v prime, v plus x v prime, and we can replace every y over x with v. We supposed y over x to be v, so we replace these y over x here and here with v. So actually here we have to subtract y prime. We replaced y prime with this because y prime is equal to this expression minus y over x. But don't forget, y over x is v, so minus v equals to cosine squared of y over x. But y over x is v, so cosine squared of v. Now, if you attention here, v and v cancel each other, so we have x v prime equals to a cosine squared of v. Now this differential equation is a separable differential equation. Note that v prime is derivative of v with respect to x. So I can write this differential equation in this form. X dv over dx. v prime is dy over dx. In this form, it is more clear that this differential equation is a separable differential equation, equals to cosine squared of v. Now, here, if we move this cosine squared of v to the denominator of dv, and we move dx to the top, and we bring x to the denominator, actually, if we do a cross multiplication, we can write this differential equation in the form of dv over cosine squared of v. We want to separate v from x. We bring this to the denominator of dv because we want dv to be with v. Every expression with v must be with dv. And we bring dx to the top, so equals dx, and x from here goes to the denominator. So we get to this separable differential equation. As you can see here, v is in the left side and every x is in the right side. So we have separated v from x. If you remember, for solving separable differential equations, we have to integrate from both sides of the equation. So for finding v, we integrate from the left side and the right side of the equation. Integral of dv over cosine squared of v is tangent of v. Note that here we have 1 over cosine squared. Cosine squared is in denominator, and 1 over cosine squared is secant squared. And from the formulas of integral, we know that integral of secant squared is tangent of v, because derivative of tangent is secant squared, and so integral of secant squared is tangent. So integral of the left side is tangent of v, and integral of dx over x is ln of x. If it's maybe better to put absolute here, but usually you can put only x here, plus c. Now here, if you want to find v explicitly in terms of x, if you want to find v without this tangent here, if you want to find v explicitly in terms of x, we have to get rid of this tangent here. Inverse of tangent is tangent inverse or arctangent. So from here, we can say v equals to tangent inverse of ln of x plus c. But don't forget, in our original equation, y is the unknown function, and we want to find y from this differential equation. So at the end, now we have to replace v with y over x. So y over x equals to tangent inverse of ln of x plus c. Now, as the last step is, if we multiply both sides of this solution with x, finally we can say y equals to x tangent inverse of ln of x plus c. So this is the solution of this homogeneous differential equation. Let me show you another example. The differential equation is 2xy dy over dx equals to 4x squared plus 3y squared. In this differential equation, it is not clear that this differential equation is a homogeneous differential equation. But note that a differential equation is homogeneous if y prime on y prime, note that in y prime the coefficient here is 1, equals to f of y over x. But here the y prime has this coefficient. So let's first divide both sides of this equation by 2xy, then we can see that the differential equation is a homogeneous differential equation. If we divide both sides of this equation by 2xy, then we have dy over dx equals to 4x squared over 2xy plus 3y squared over 2xy. So here we divide both sides of this equation by 2xy. The left side, 2xy and 2xy cancel, only dy over dx remains. And we divide every term in the right side by 2xy. Now, if we simplify these fractions, in the first fraction, 4 and 2 cancel each other, a 2 remains in top. X squared in numerator with 1x in denominator cancels. So, if we simplify this, we have 2x over y. And here, if we simplify y with y squared, a y remains in top. So we have 3 over 2 times by y over x. Now here you can see that we have y over x in this term, and in the other term we have x over y, which is the reciprocal of y over x. So if we suppose y over x to be v, we can replace this x over y with 1 over v, because this is reciprocal of y over x. So now it is clear that this differential equation is a homogeneous differential equation. So we suppose v to be y over x. This is how we solve homogeneous differential equations. Always we suppose y over x to be v. Then from here y is xv, and from that we can conclude that y prime derivative of y equals derivative of x, which is 1 times v plus x times v prime, as we did in the previous example. Now if we replace this y prime with this, so we have v plus x v prime equals to, again note that because we suppose y over x to be v, x over y is the reciprocal of y over x, is 1 over v. So we can replace this with 2 times 1 over v, or 2 over v actually, plus 3 over 2 times v, because y over x is v. So with this substitution, we get to this differential equation. Now here, if we move this v to the other side of the equation, to simplify the differential equation, we have x v prime in the left side equals to, this term is 2 over v plus 3 over 2v minus this v. This equals to 1 over 2v, because this v is actually 2 over 2v. If you do a common denominator, 3 minus 2 is 1 over 2. So 3 over 2v minus v equals 1/2 v. So finally, with the substitution, we get to this differential equation. If here we do a common denominator between these two terms to make them one fraction, we have x v prime equals to, the common denominator between these two terms is 2v, and then with this common denominator, in numerator of the first one we have 4, and in the other one we get v squared. So let me show you how I did this common denominator. The first term was 2 over v, the other term was v over 2. Here between these two terms the common denominator is 2v. If we multiply this by that we get 4, and if we multiply v by v we get v squared. So we get to this expression. Okay, let's back to our differential equation. Now if we replace this v prime here with dv over dx to separate v from x, let me change the color. So we have x times dv over dx equals to 4 plus v squared over 2v. We want to separate v from x, so we bring everything that is here to the side that dv is, to the left side, and we bring these to the other side. For doing this we have to do cross multiplication. 2v goes top and this goes down to the denominator. Dx goes to the numerator of the other side, and x goes to the denominator of the other side. So after doing this we get to this differential equation: 2v dv over 4 plus v squared equals dx over x. So again let me show you what happened from here to here. 2v goes up like here. This goes to the denominator. So we have 4 plus v squared. And because we want to separate v from x, dx goes up to the numerator and x goes down, as you can see here. Now for solving this separable differential equation, we have to integrate from both sides. Integral of the right side is obvious. Integral of dx over x is ln of x. And the integral of the left side of the equation is ln of 4 plus v squared. If you wonder why this integral of this equals to this, so for solving again this differential equation, we integrated from both sides. We integrated from left and right, and we get to this. And don't forget to add a c to the left side or right. But why this integral equals this? With a simple, really simple substitution, use substitution, you can see that the integral of this equals that. For example, if you choose this to be u, du is 2v dv, which is exactly up there. So we have du over u, and the integral of du over u is ln of u, and u is the denominator, so the integral of 2v dv over 4 plus v squared is this. And integral of dx over x is ln of x. Now here, immediately you can replace this v with y over x. Note that v is a substitution that we use for solving the differential equation. At the last step, always we have to replace v with the original variable. But before doing that, it's better to simplify this answer and write it in a better form. Let me show you how you can do this. I want to find a way to get rid of these ln's. There are different ways that you can do this. I will show you one of the ways that you can get rid of these ln's. Because this term and this term, both of them have ln, and here I have a constant. Instead of putting simple c here, always I can replace c if it is helpful. Instead of putting c here, you can put ln of c. So again, why I am doing this, why I'm not just putting c, because when we integrate we have to add a c. But why here instead of putting c I prefer to put ln of c? Because the other terms have ln, and if I replace c with ln of c, note that c is not ln of c, these are different. But anyway, any c can be ln of another constant, so I can do this. This is one of the techniques that at the last steps of solving differential equations, you can see this technique. So we use ln of c instead of c. But what is the benefit of this? Now note that because this term has ln and this term has ln, we can add them and write them as ln of cx, because note that ln has this property, ln of a plus ln of b is ln of ab. So we can write this as ln of cx. So we get to ln of 4 plus v squared equals ln of cx. Now, if we cancel ln with ln from both sides of the equation, because ln of this expression equals ln of that expression, so the two expressions must be equal to each other. In this way, we can get rid of ln. So we get to this 4 plus v squared equals cx. Now here, if we replace this v with y over x, we have 4 plus y over x squared equals cx. Y over x squared is actually y squared over x squared, which if we multiply both sides of this relation by x2 to get rid of this x2 in denominator, we can write our final answer in this form. Let me zoom in a bit here again. So we can write the final answer as 4x2 plus y2 equals cx to the 3. So this is the solution of this differential equation. So from here to here, I multiply both sides by x2. Another way that you can convert this to this, if you don't like this ln of c technique, if you want to see another way that how you can convert this to this, is to note that when we integrated from both sides of this equation, we get to this relation. I want to show you another way how we can get rid of ln's if you need to know this technique. So we have ln of 4 plus v squared equals ln of x plus c. How we can get rid of these ln's? Another way that you can do this is to say, because ln of this expression equals ln of x plus c, we know that we have these rules. If ln of a equals b, to get rid of this ln, we can say a equals e to the b. If we use this, so we can say 4 plus v squared equals e to the power of this. So e to the power of ln of x plus c. So we use this technique. ln of a equals b, then a is e to the b. Now, Let's simplify this. E to the ln of x plus c is actually e to the power of ln of x times e to the c. E to the ln of x is x, because we know that e to the ln of any expression equals the same expression. So this is x. So we have 4 plus v squared is x. And e to the c, because e is a constant and c is a constant, again we can name it another constant. So it's, if we make this to be c1 first, we can name, suppose all of this to be c. Now compare this with this, you can see that they are the same. 4 plus v squared equals cx or xc. This is another way that we can get rid of these ln's in the equation. And you have to know these techniques for solving differential equations. In solving differential equations, we are playing with ln function and exponential functions a lot. So it's better to be familiar with the properties of these functions. Especially ln is very important. Let me show you another example. The differential equation is x times dy over dx equals to x tangent of y over x plus y, and we want a solution of this differential equation that passes through this point. Y of 2 equals pi. So we want the solution of this differential equation that when x is 2, y equals pi. First, we divide both sides of this equation by x to make it something like y prime equals f of something. So, to make coefficient of y prime 1, first we divide both sides by x to get rid of this x here. So, if we divide both sides of this equation by x, we have dy over dx equals to tangent of y over x plus y over x. If we divide this by x, x and x cancel and only tangent of y over x remains, and if we divide y by x, we have y over x. In this equation, it is completely obvious that this differential equation is a homogeneous differential equation because we have y over x here and here. So we suppose y over x to be v, and so from here y is xv, and from that y prime, derivative of y equals derivative of this, which is v plus xv prime. Now if we replace this y prime with v plus xv prime, we have this equals to tangent of v plus v. V and v cancel each other from both sides, so xv prime is tangent of v, and because v prime is dv over dx, so we have x times dv over dx equals tangent of v. If we move this tangent of v to the denominator of dv, and if we bring dx to the top of the other side and x to the denominator, finally we have dv over tangent of v equals dx over x. Integral of the right side is obvious. Note that this differential equation is a separable differential equation, and for solving separable differential equations we have to integrate from both sides of the equation. So we have to find integral of this and integral of this. But integral of the left side of the equation, how we can find integral of dv over tangent of v? Note that tangent of v is sine over cosine, or let me show you another. 1 over tangent, because tangent is the denominator, 1 over tangent is actually cotangent of v. We know this. And cotangent is cosine over sine. Another way that you can show that this equals cosine over sine is to know that tangent is sine over cosine. And 1 over sine over cosine is the reciprocal of this, which is cosine over sine anyway. For finding integral of this, we can say integral of dv over tangent of v is the same as integral of cosine of v over sine of v dv equals integral of dx over x. Integral of the right side of this equation is ln of x. Don't forget to add c. But what is integral of cosine over sine? Again here, similar to the previous question, if we suppose this to be u, derivative of this u is exactly in top. And when derivative of the bottom is exactly in top, with a simple u substitution, we get to du over u, because we suppose this to be u, so we have u, and all of the numerator is du, derivative of u. Integral of du over u is ln of u, and u is sine of v. So finally we get to ln of sine of v equals ln of x plus c. Here immediately we can replace v with y over x, but I prefer to, again similar to the previous question, simplify this. We can get rid of this c with the same method. Here I'm using the other thing. First, instead of c, I put c1 here. Ln of sine of v equals this, so I can say sine of v equals to e to the power of ln of x plus c1. So sine of v equals to e to the ln of x times e to the c1. And we can name all of this another c, because everything here is a constant. E is a constant, the power is a constant, so all of this is a constant. So finally, we can write our answer as sine of v equals e to the ln of x is x, and this is a constant c, so we can write this as x times c or cx. Don't forget the v is y over x, so this is the answer, the general solution of this differential equation. But in this equation we had an initial condition. We want to find c such that when we put 2 for x, y equals pi. So sine of pi over 2, don't forget y is pi when x is 2. Sine of pi over 2 must be equal to c times x, and x is 2. C times 2. Sine of pi over 2 is 1. So all of this is 1. So c is 1 over 2. And so we can write the final solution as sine of y over x equals to, because c is 1/2, equals to 1/2 x. And if you like here, you can find y explicitly in terms of x. You can easily get rid of this sign by taking sine inverse of the other side, and then you multiply both sides by x. Let me show you how. If you want, you can write your answer as y over x equals sine inverse of x over 2, or 1/2 x. And finally, if we multiply both sides by x, we have x sine inverse of x over 2. I hope by watching this video you have learned how to solve homogeneous differential equations. If you like this video, please subscribe in my channel and see you in the next videos. Thank you for watching.